Hello, this is Mr. McMurray, and we're going to talk about momentum today. All right, momentum notes. We're going to gather some momentum, get some momentum going here, hopefully. We may have, remember we talked about, inertia. And inertia is we said that inertia has to do with mass, and we said that, for example, say you have a semi-truck going 60 miles an hour down the road, and a semi-truck parked on the side of the road, they would have exactly the same inertia because inertia just has to do with how much mass there is. And they have the same mass, no matter how fast they are going. Now, obviously things would happen differently if you stepped out in front of a 60 mile per hour semi-truck and if you walked out in front of a parked semi-truck. So that has to do more with momentum, and that's what we're going to talk about today. Momentum is inertia or mass in motion. Okay, so now it is moving. All right, and just real quickly, we're going to talk about this. We'll come back to it later in future notes, but momentum is conserved for all interactions where external forces don't interfere. In other words, if you just let them go on their own, that momentum will always be conserved. All right, and so for an example, let's just look at our Newton's cradle. All right, now with the Newton's cradle, we take one weight over here, it has a certain amount of mass, and it's moving at a certain speed. When we hit it, it hits the other side. Now when it comes out to the other side over here, it takes off with the same amount of mass and the same amount of speed. And so we are conserving the momentum, the mass times the velocity. And so if we have the same mass, it will hit the other side and go off at the same speed. Now, the one that comes down will stop. Why? Because when it hits this, it has the force it exerts this way, and it will exert just exactly the same and opposite force on that way, which will stop it cold. Okay, that's Newton's third law. For every action force, there's an equal opposite reaction. Now, the momentum from this ball gets past the middle ball, which gets past the last ball, and it will fly off. Since it is the same weight as this ball over here, it will have the same velocity also and fly off at the same speed. Then it comes back and the same thing. If you repeat it, it goes back this direction, makes it fly off at roughly the same speed. Now, because of friction, it would not be exactly the same speed, so they get slower and slower and eventually would stop. But that's basically the idea of conserving momentum. All right. Now, if one of the balls was bigger, twice as big, and it came down, when the other ball came off the other side, if it's half as big, it would be going twice as fast. So you'd have the same amount of momentum. If the small ball came and hit it, then the big ball would go half as fast because it's twice as big or has twice as much of the mass, so that you would have the same amount of momentum each time it hits and goes back and forth. Okay, but more about conservation of momentum later. All right, so for now, let's go to this. All right, the formula for momentum, which we kind of already hinted on, is momentum equals mass times velocity. So if you want to know how much momentum something has, you take the mass, which would be measured in kilograms, times the velocity, which would be in meters per second. So it's going to be kilograms times meters per second, right? And that would be momentum. Now, in terms of formula, the formula would be P for momentum equals mass times velocity. Now, someone says, why would the letter P be the word for momentum? Well, one, momentum, there's already mass, there's meters, there's millimeters, there's mm. So there's already a lot of M words. But actually, when Newton and Galileo and some of the other people started talking about motion, they didn't use the word momentum for this. We've used that since then. At the time, they used the word impetus. If there's an impetus for you to do something, is there a push or a prompting to make you do something? Okay, and that's your impetus. Okay, and so your impetus is your push or something that pushes you to do something. And so the Latin word for impetus starts with a P, similar to the word we have push, and so that's why we ended up with the letter P, just for your information, in case you're wondering how did that happen to come about. All right, now momentum is a vector quantity, which means it has direction as well as magnitude. If I push a bowling ball, it has a direction as well as a amount. We can take the mass up here times its velocity, that would give us the magnitude or the number, and then we would also have a direction. Now, usually when we talk about momentum, we usually are going to talk about positive or negative. All right? We're more worried about, is it going forward or is it going backwards? Now, which direction's forward, which one's backwards, which one's positive, which one's negative, it doesn't really matter. As long as you say one direction is positive, the other direction needs to be negative. But in general, we tend to say if you go to the right, we say it's positive. If you go to the left, backwards, so we say negative. It could be just as well the other way around. Okay? Probably just one of those biases that right-handed people had until they started it. All right. Now, if you want to improve the momentum or increase the momentum of an object, you could do it by increasing the mass or the velocity. And both of these, if you increase the mass, it will increase the momentum. So this is a direct relationship between mass and momentum. Also, though, if it goes faster, it will also have more momentum. So both mass and velocity have a directly proportional relationship to momentum. If you double the mass, you double the momentum. If you double the velocity, you double the momentum. If you double the mass and double the velocity, that'd be 2 times 2, it's going to be 4 times as much momentum. Okay? So there is no inverse in this case because there's no fraction involved. So momentum is directly related to the mass and the velocity. So you can have a large momentum if, one, the object's mass is large. If it's large, then it's going to have a large momentum, big mass. You have a semi-truck versus a Volkswagen Bug. Okay, the semi-truck is going to have a lot more mass. So already it has a heads up in the momentum graph. However, it also depends on the velocity. So if the speed is large, then it could also have a high momentum. For example, if the Volkswagen Bug is going 150 miles an hour and the semi-truck is only going 50 miles an hour, you could have maybe where the Volkswagen Bug could have the same momentum or even more momentum if it's going fast enough. So mass is large, and if you make the speed a large amount. Obviously, if you want to really increase the momentum, you can just increase the mass and the speed. All right, so the bigger object, the faster it's going, it's going to have more momentum. So, for example, a lineman running at a certain speed will have more momentum than a running back running at the same speed. However, a lot of times the running back will run over the lineman if he has a higher speed to make up for his lower mass. All right? So that's kind of how that relates to momentum. All right? Now, an example of this, though, would be like an oil tanker. Oil tankers are like, I forget how many football fields long and football field wide. They're very, very, very big ships. And then they're filled full of oil, so they have a lot of mass when they're full. Now, if they're coming from Saudi Arabia, they have to hit a pretty good speed. I don't know, I'm just guessing a couple hundred miles an hour, between around 100 miles, maybe a little less. But they have a pretty decent speed, which means together with their large mass, they have a pretty big momentum. And so when they get close to shore, they have to basically turn off the engine 25 miles away from port and coast the rest of the way in. So by the time they get to the coast, they will be going slow enough that they can maneuver carefully around the harbor and get into where they need to go and not run over things. Otherwise, they're going to be going so fast they can't slow down. They're going to smash right into the shore, spill oil all over the beach and the ocean, and do lots of damage. Okay, so they have to slow down. Same thing for a train. Trains, if they see you on the train track, by the time they see you, there's no way they can stop. Okay, they have so much momentum, especially if they have lots of cars and they're full of, say, coal, filled up with rock or coal or something like that. They have so much mass and they've got a pretty good speed. There's just no way that they're going to be able to stop. Okay, and I've talked to an engineer once and he said it's really tragic and it really scars kind of the engineers when they hit a car, but it happens because there's just no way they can stop in time. They have so much momentum. All right. Now, say we want to change the momentum, either to stop it, in that case, of trying to stop a train or stop a oil tanker, or maybe we want to speed it up. Either way, if we want to change the momentum, it takes what we call impulse. Okay. Now, impulse can mean, oh, you're going down the shopping lane and, oh, there's a candy bar. I think I'll buy one of those. That's an impulse, but that's not the kind of impulse we're talking about here. Okay. If we want to change the momentum, first of all, we are usually going to change the velocity. We could change the mass. Okay. If you were a truck going down the road and all of a sudden a weight dropped into the back bed of your truck, then that would change your mass. But most of the time, the mass is pretty well set, okay, for the object. And so what really changes, other than loading or unloading an object, is the velocity. So a lot of times when we're talking about changing the momentum, and that's what delta or triangle P means. Delta P means change in momentum. It's equal to the mass, which is usually going to say the same, times the change in velocity. All right. Now, if the velocity changes, we know that is called, that's right, acceleration. And so anytime the momentum changes, it's usually because the velocity changes, and that means that there is acceleration going on. And we know If the mass is staying the same, the only way something can accelerate, according to this formula, is if the force increases. Okay? There's a net force acting on the object. And so in order to change the momentum, we have to have a force. Okay? Because we know that's directly proportional to the amount of acceleration. All right? So the greater the force acting on an object, the greater it's going to accelerate. The more it accelerates, the greater the velocity changes, either speeding up or slowing down, or possibly changing direction. And therefore, the greater the change in momentum is. Okay? And so we change force, which changes the acceleration, which changes the velocity, which means that there's a big change in momentum. As it goes faster, for example, it could gain momentum. If it goes slower, it would lose or have less momentum. All right? And that's kind of what impulse is. Now, besides the amount of force that we put on something, it also depends how long the force acts on the object, okay? So, for example, if you hit a golf ball, or you hit a tennis ball with a tennis racket, or a baseball with a bat, doesn't matter. But there's two things. One is how hard you swing and hit the ball, okay? For example, if you bunt it, you just barely kind of tap it, and you don't hit it very hard, there's not much force exerted. It also depends, though, in any of those sports, the coaches will always tell you to follow through. Why follow through? Because you hit the ball, your bat is in contact with the ball, or your racket or your golf club is in contact with the ball for more time. So how long the force acts on the object is also important. Okay? If you can't increase the force, you can only hit the ball so much harder when you lift weights, do whatever, but you can only hit the ball so hard, so you can't change the amount of force you exert on it, then you can change the amount of time that you come in contact with. Okay? So if you exert the same force over a longer period of time, then you're going to have a greater change in momentum, which is what you want when you hit a baseball or a tennis ball or a golf ball. You want it to change momentum and speed up in the other direction. Okay? And so it's going to change direction, and then it's going to speed up in that other direction. Okay? And so that's what you want. So those two things are what control the impulse. Okay? And the formula then for impulse is J equals force, or net force, if you want to think of it that way, times T. Don't ask me why there's a little square right there. I don't know. I tried to get rid of it. Trust me, I did. It has to do with going from a MacBook to a Dell, apparently, and it won't let me get rid of it, but it won't. Yeah, anyhow, never mind. But anyhow, that's it. Force times time. And by time here, we mean the time that you're actually hitting the ball. For example, if I punt a football and it hangs up in the air for, I have the hang time of 4.8 seconds or something before it comes down and it's fair caught, the force would be how hard I hit the ball with my foot, okay? Because that's the only time I'm exerting a force. Once it leaves my foot, the only forces acting on it are gravity and air resistance, okay? I'm not exerting a force on it anymore. The other thing is how many seconds do I come in contact with it, with my foot. Not how long is it in the air, because I'm only exerting the force on it while I'm touching it. So the time is only while I'm touching it and exerting that force. Okay? Now, once again, that may not seem like a big increase. Maybe it goes from 1/10 of a second to 3/10 of a second. But that's the key. 3/10 of a second is 3 times as long as 1/10 of a second. And so you're going to change the momentum 3 times more if you can hit it for longer. Okay? Now, impulse is equal to force times time. Okay, that's just writing it out in words, okay? But why is it J and not I? I have no earthly idea, okay? If you find out, let me know. All right. Now, the question is, what units would we have? Well, force, which is right here, we said force would be in newtons, okay, times time, which is going to be officially in seconds. Okay, so Newton seconds would be an acceptable unit, but that really is not the most condensed, because newtons are kilograms times, or mass times meters per second squared. That would be newtons, and then times seconds. Okay, well, when you cancel this seconds would cancel out with one of these. And so your units would be kilograms times meters per second, or mass times velocity. And that's basically what the units would be. So we can use Newton seconds or kilograms times meters per second. Kilograms times meters per second is more useful when you're trying to cancel and divide in a problem, but Newton seconds is easier to write. Okay? And that's all we're going to talk about today. Next time we'll talk on